Okay, in these videos, we're going to study rotational dynamics. Okay, and so we're going to start this by understanding what torque is. So consider this simple picture where we have, you can think of it as a rod or any object that's pivoted at this point. So this is where we have the pivot, we call the pivot P, and we're exerting a force at a distance R from this pivot, and such that this force makes an angle theta with R. Okay, and this could be the force that you use to open a door, close a door, where you're exerting a torque, and many other situations. So our goal is to define torque in terms of all these things. So what is torque? Okay, so torque itself is a vector. It is written as R cross F. Okay, and we can write down the magnitude of this vector as simply R times F times sine of theta, using the definition of a cross product. And this also, the cross product also gives us the direction of the torque. And what we know is that torque, first of all, is always perpendicular to both R and F. So it is always perpendicular to the plane formed by R and F. And the way you get the direction is by simply using the right hand rule, which says that if you were to rotate the vector R, okay, so if let's say R in this case is pointing here and say F is pointing here, okay, in this direction, if you were to rotate R into F, okay, then the torque would be pointing out of the plane of this paper. Okay, so it would be pointing out. If you were to look at this from a 3D picture, if I have my R here and if I have my force vector pointing here, so this is R and this is F, okay, they're both vectors, then when you rotate R into F, okay, your torque points in the direction perpendicular, and this direction is given by the right hand rule. This is also how the coordinates are labeled. Okay, the X, Y, and Z coordinates, they also follow the same right hand rule. Okay, so this is what we'll use to figure out the torque. Now there is another way of looking at the torque. Okay, and in order to do this, let us consider. Okay, so if we look at the original picture that we had, okay, if we make a couple of adjustments to this picture, we'll be able to look at what this alternative definition for torque is. So the first thing we'll do is we can extend the force. Okay, we just extend it wherever the pivot is, or just completely draw the continue to draw the force, and then what we can do is drop a perpendicular from the pivot to this force. So draw a perpendicular from here, and when we draw this, what we notice is that if we have a simple right angle triangle here, and this particular side of the right triangle, okay, which also is the perpendicular distance, is simply equal to R times sine of theta. So this definition actually makes life very easy in a lot of cases. Okay, and what we can do is we can write tau also as R perpendicular times F, which is simply the perpendicular distance of the force from the pivot. Okay, in the example, the first example that we will solve, we look at the advantage of this particular definition. All right, so far what we have is we have torque whose magnitude is RF sine theta, okay, where theta is equal to the angle between the force and the radius vector. Okay, now this equation also tells us conditions when the torque itself is non-existent. Okay, so let's just explore that very quickly, and then in the next video we'll look at our first example. So here, one of the things it says is that theta is 0 or 180 degrees, there will be no torque. Now to see this very clearly, if you look at this picture once again, theta equal to 0 would mean a force pointing in this direction, and clearly this force is not going to produce any kind of rotation. And on the other hand, if theta was 180, okay, the force would be in this direction. Once again, there would be no rotation. So here tau is equal to 0, and this is another example where tau is 0. Now another important example which we will use as we discuss equilibrium conditions and stuff is if the force is acting right at the pivot. So let's say if this is the pivot point, and my force F is simply pointing here. So here, okay, the torque about my pivot is also going to be equal to 0, because there is no way this force can cause any kind of rotation. It's basically saying that you wouldn't be able to open or close a door by exerting forces at the hinge. Okay, it's just not going to create any kind of rotation. So keep these few things in mind. It's going to become very essential, important tools when we start talking about equilibrium cases. Okay, so once again, torque is equal to Rf sine theta, or R perpendicular times F, and understand the cases when torque is equal to 0. In the next video, what we'll look at a simple example, and we'll learn how to calculate torques.